Hello, welcome to my today presentation about RFIC module design 1 for MMIC amplifiers. I am Mohammed Robiul. Currently, I am working as a research assistant under supervision of Professor Jeong Park, and I am also a fourth semester student at Kangwon University. My research research interest on mainly triboelectric nanogenerator for cell power sensor application. Today I would like to discuss about RFIC module design 1. First of all, I would like to mainly overview of RFIC module design of MMIC amplifier. First of all, the amplifier is an essential component of wireless communication system. The basic theory of MMIC amplifier is including mainly description of DC bias injection, classical stability and analysis, and also discuss different types of noise such as thermal noise, short noise, flicker and popcorn noise, and briefly review. And lastly, I would like to discuss about the practical design of MMIC IF amplifier, the cascade, no noise amplifier, and different stages of power amplifier are illustrated later. Here discuss about DC bias injection. Mainly the transistor must have DC bias to operate and can be set to an operating point to show uh, IV characteristics. From figure 3.1 it shows the schematically the IV curves of generic field effect transistor, indicating the four most common operating points used for amplifier. First, mainly IDS is the saturated drain current, and then point 1 represents the no noise operating point, and point 2 it shows the FET is operated with VGS close to 0 voltage and IDS close to, and here ID is close to IDSS, and at point 4 this one, at this point bias point, the FET gives its maximum small signal gain. Here the high DC power consumption and increased noise figure tend to make the operating point unattractive. Point 3 is placed almost exactly in the middle of IV curve, allowing the maximum linear output power to accept for class A operation. For higher efficiency, although the linearity will be degraded, an operating point 4 can be used for class AB operation of amplifier. Here the DC gate and drain DC bias voltages can apply to FET in number of methods are illustrated in figure 3.2, where inductor as a bias chokes, high value resistors, microstrip stubs, self biasing. In method A, inductor as a bias shock, the drain voltage is required to be positive and the gate voltage is required to be negative. And it's very convenient to find a topology with shunt inductor through which the bias can be applied. In method B, that's called high value resistors are used to apply the bias voltages. With the exception of low noise and high power amplifiers, this is very suitable technique for establishing the gate bias because the gate draws no current and the resistor can be stabilize the device. And method C. Microstrip stubs. Here short circuit microstrip stubs are used. The short circuit end is ground with a decoupling capacitor so that the DC bias can be applied. In standalone elements, the bias lines would have to quarter wavelength in length, which would be too large for the most cases. In method B, that's called self-biasing technique used, enabling the FET to bias from a single power supply rail. And here another method, active load method. It illustrates the well-known active load technique, in which active load has zero gate source voltage and hence operates at its saturated drain current. The active loads presents a large resistance in parallel with small capacitance. It causes some reduction in the gain as a result, but is very compact and suitable for high packaging density and DC coupled amplifiers. Method F, constant current source self biasing. This technique, the gate of amplifier FET is set at 0 voltage, but its source is raised to a positive DC voltage by the drain sources voltage of the current sources FET. Thus the gate source voltage is negative and the amplifying device runs an IDSS of the current source FET. Finally, the DC coupling method, level shifting diodes are used to lower the DC output voltage of one stage down to the input voltage of the following stage. This technique is used for DC coupled amplifier, and source stabilization are shown in figure A. A source stabilizer resistor can be added to the desired circuit. Another thing, classical stability and gain analysis. The stability of amplifier is a important consideration in designing and decide based on S parameter of active devices as well as matching and termination. Stability consists of two conditions. First, unconditional stability. This means the total circuit does not oscillate when any matching network or termination is added. Another thing is conditional stability. The total circuit either can be stable or can oscillate under any condition. Here you can see the equation, all coefficients are normalized to the same value. Here the circle is known as load stability circle. Through the Smith charts illustrating the stable and unstable region in the torus plane, and it can be either partial inside the Smith chart and completely inside the Smith chart or completely outside the Smith chart. Whether the stable region is inside or outside the circle can be determined by inspecting the location of the origin, because the point is right in the stable region. Figure 3.5 shows the stability cycle based on Smith chart, and figure 3c the condition of unconditional stability, and methods for how to improve the stability. That's why here I'd like to discuss about how to improve the stability. Here different types of method to increase the stability, like resistive loading, feedback method, and so on. First of all, resistive loading. Here figure 3.7 is resistive loading for stability. Transistor stability can be improved by adding small series or large shunt resistor to input output. That's shown 3.7. The designer should ensure the connection of resistor in series or shunt. The addition of resistor yields a trade-off in noise and gain. And In case of feedback method, most amplifiers incorporate some form of feedback. It is interesting to note that the theory of negative feedback has been developed by electronics engineers. Feedback can be either negative, that means degenerative, and positive, this means regenerative. The negative feedback is applied to this amplifier design. And power gain equations, the transducer power gain GT and the power gain GP, also called the operation power gain, the available power gain GA. From this figure 3.8, a diagram of microwave amplifier. Here input matching network GS and active device block and output matching network with load resistance. Here mainly several power gains expressed with the equation, mainly power delivered to the load by power available from the source, and power delivered to the load and power input from the network, and power delivered to the network by power input from the sources based on different terms here expressed, and the parameter of active devices. And noise consideration, mainly the sensitivity of communication system is limited by noise. The broadcast definition of noise is specified as everything except the desired signal. However, the source of noise remained mysterious until H. Nyquist and J. B. Johnson and W. Schottky published investigation on the origin of noise, including assessment of how much noise one can expect. Now discuss about thermal noise. Johnson was the first to report of noise in register, and Nyquist explained this thermal noise through the measurement of Brownian motions. The thermal noise is often called Johnson noise or less frequently Nyquist noise, and the thermal noise power is exactly proportional to the absolute temperature. Hence, from this equation, K is the Boltzmann's constant, T is the absolute temperature in Kelvin, and del F is the noise bandwidth in Hertz over which the measurement is carried. Another noise is short noise. Short noise is granular, granular, granular nature of electronic charge. Two conditions must be satisfied for short noise to occur, mainly direct current flow, potential barrier over which the charge carriers can hop, and the short noise current should depend on the charge of electron, the total DC current flow, and the bandwidth. And another noise is flicker noise. Mainly flicker noise is a type of electronic noise with 1 by f power spectral density. It is therefore often referred as 1 by f noise or pink noise. It occurs in almost all electronic devices and can show up with variety of effects such as impurities in conductive channel, generation, regeneration, due to mainly transistor due to base current, and so on. Another is popcorn noise, is a type of electronic noise that occurs in semiconductor and ultra thin gate oxide films. It consists of sudden step-like transition between two or more discrete voltage or current levels as high as several hundreds microvolts at random and unpredictable times. Each shift in offset voltage or current often lasts from the several microsecond to second and sound like popcorn popping if hooked up to an audio speaker. IF amplifier design. Here figure 3.10, a block diagram of LNB, that means low noise block, and the LNB has function of converting frequency from satellites to the set top box. The converter accepts an radio frequency input to 11.71 to 12.75 GHz and generates an IF output 1032 to 2072 MHz. The local oscillator frequency is 10.67 GHz, and the linearity, noise removal, and frequency compensation and amplification performance parameter of LNB down converter is satellite broadcast. IF amplifier design. If IF amplifier boosts the signal to reasonable input level for the setup box, it is worth noting that the system impedance in area is 75 ohm and not 50 ohm. In a down converter, the IF amplifier compensates losses in the mixer and filter in addition to providing additional gain and flat gain response over broad bandwidth, and this is performed to ensure good linearity and positive gain slope with increasing frequency in the IF amplifier, helping to compensate for negative gain slope of coaxial cable and other RF front-end blocks. Indium gallium phosphate HBT characteristics. The HBT device parameters for high linearity mainly beta factor of 115 and FT of 50 GHz and frequency maximum of 80 GHz. The breakdown voltage BB of 13.8 volt and BB CBO of 23.5 volt and BB EBO of 7.2 volt. Twisters broadband IF amplifier design. Here figure 3.11. Simplified schematic of amplifier here in input. This block diagram shows input matching, inter-stage matching and output matching and output. Amplifier bandwidth range of 1 to 2 GHz. The main objective of this design is to achieve flat gain for broadband. The twisted broadband IF amplifier was designed to obtain a specific value of gain, bandwidth, and flatness. Stages are used in common emitter configuration for broadband IF amplifier to allow for a voltage divider bias to provide bias point stabilization. Each stage has resistor with established constant DC current in emitter of. The ratio of current gain is beta factor equal to collector current by base current, approximately emitter current by base current. Cascade LNA design. Here figure 3.16, a block diagram of KU band LNB as super heterodyne front end. This block diagram shows super heterodyne front end. Here RF signal is input after filtration and is in mixing and IF amplifier, and we get IF signal. Integrating the image reject filter into a cascade low noise amplifier, the performance is excellent in terms of image rejection ratio at the nodes, simple tuning and minimization of noise contribution of nodes. The technology is completely integrated with the use of on-chip based collector junction diode. Power amplifier design. A system component whose main task is to increase the power level of the signal at its input and predefined level. In terms of small signal gain, the absolute output level is the main feature of power amplifier. This one mainly 3-stage power amplifier design. Input matching, first stage, inter-stage matching, then second stage, then again inter-stage matching, third stage, and finally we got output matching. Power amplifier design 1. Here the devices typically operate under large signal regimes, forcing the exploration of nonlinear operating regions. This section presents a 1 volt power amplifier for CDMA using indium gallium phosphate or gallium arsenide HBT technology. The output power is higher than 31 decibel, and the first stage uses F20 into 20, and the second stage is made of 22 transistor, and third stage configured into 48 cells. This one mainly the block diagram of an energetic schematic representation of power amplifier operation. RF input as a PIN, and this one a power amplifier, and we mainly provide the DC power PDC, and finally we get RF output power Pout. DC power from the PDC into the mainly power amplifier, then we got mainly microwave power Pout by driving PIN input power. And mainly when we measure the efficiency is called drain efficiency or collector efficiency, as given by the mainly Pout by PDC into multiple 100%. Thus we got the drain efficiency on collector efficiency. And thank you to all to watch my video.